Artificial intelligence development is frequently discussed as a software-only problem, focusing on the isolated logic of search algorithms. Modern deployment requires mastering three distinct layers of logic and hardware, a structural framework known as the AI stack. The first tier is the software foundation. This is the level where specific programming languages establish the logic and mathematical boundaries for the entire system. The middle tier is the application layer. Here, raw foundational code is structured and trained into functioning neural networks. The final tier is compute infrastructure. These massive networks require specialized cloud hardware to physically execute their operations. Understanding AI means tracking how a single line of code travels upward through this stack to eventually command custom silicon. At the base layer, the programming language an engineer selects dictates the processing capabilities and limits of the system. In 1958, John McCarthy created Lisp. It was engineered specifically to process symbolic information, featuring the dynamic creation of objects and automatic garbage collection. Alongside Lisp, Prolog provided efficient pattern matching and tree-based data structures, utilizing automatic backtracking to run early expert systems. But as AI development moved toward deep learning, the computational requirements shifted. Systems needed to process heavy scientific computations rather than pure rule-based logic. Python emerged to manage this data. Its readable syntax requires significantly shorter development time than older languages like C++ or Ruby. This language relies on specialized libraries like NumPy for scientific computation and PyBrain for immediate machine learning frameworks. For statistical analysis, engineers utilize R programming to manipulate data and render publication-quality plots through packages like RODBC and gmodels. Java remains a distinct choice for large-scale projects, providing package services and integrated toolkits like Swing and SWT for sophisticated graphical interfaces. This migration from Lisp to Python and Java mirrors a shift in the field, moving from symbolic logic to massive mathematical processing. Once that logic is established in Tier 1, it builds the second tier, the operational models. Deep learning is a specific execution of these models, utilizing artificial neural networks that mimic the structure and function of the human brain. The demand for these models is high. Jobs involving deep learning expanded 35-fold between 2015 and 2017 alone. One application where deep learning is currently at its peak is facial recognition. These applications identify individuals by mapping specific facial feature patterns from digital images. Facebook utilized this through their DeepFace program, tagging users' family and friends across billions of uploaded photos. Consumer mobile devices, like the iPhone X, integrated this facial recognition as a secure biometric password. However, running these personalized biometric models requires millions of rapid calculations, a load that easily overwhelms standard consumer hardware. This creates a physical computation bottleneck at the third tier of the stack, when an AI model performs tasks like object detection. Even advanced traditional CPUs are not fast enough to train these modern models. This illustration shows a standard motherboard, but the CPU at the center has reached its limit. This requires specialized AI-enabled chips to bypass standard processing constraints. These specialized architectures include application-specific integrated circuits, or ASICs, and field-programmable gate arrays. Manufacturers like NVIDIA, Intel, and Qualcomm optimize these chips specifically for computer vision, speech recognition, and natural language processing. Because these components are complex and expensive for individual users, they are housed in hyperscale cloud infrastructure. This physical infrastructure is provided by hyperscale leaders like AWS, Alibaba, Google, IBM, Microsoft Azure, and Oracle. The cloud computing market will cross $200 billion to support the hardware needs of these high-performance AI workloads. The most efficient Python code is unusable without custom silicon in a massive data center to execute it. We now have a completed stack: Python syntax building deep learning applications, which are executed on ASIC-accelerated cloud hardware. But an invisible layer governs every other part of this system: privacy and policy. As AI systems scale personalized advertising and biometrics, users often lose track of how their digital information is being utilized. The 2018 introduction of GDPR was a direct response to these concerns, establishing international regulations for data access and transparency. Countries worldwide are now working on strategies to guarantee safety and awareness in these complex technologies. To deploy AI successfully today, an engineer must optimize their logic for the software, their math for the silicon, and their data for the law.